Hello everyone again, and this is the lecture 12. And in this lecture, we're going to talk about new concepts in Java. And particularly, we'll talk about the concept of generics. In the second part of the lecture, we'll talk about functional programming and the tools that we use to implement functional programming paradigm using the Java objects like Lambdas and streams. So first of all, let me introduce you about the agenda today for today. So we'll talk about the generic collections, things that you've been already working with, but we'll have a little bit of a formal, proper introduction to the available collections in the Java standard API. And we'll also talk about type wrappers and the concepts of boxing and unboxing. And then we'll discuss about the generic methods and generic classes. And in the second half of the lecture, we'll discuss about the fundamentals of functional programming, what it is, and how Java actually implements this paradigm of programming translates this paradigm of programming into its own object-oriented representation. And what kind of constructs it uses in order to implement such paradigm, like Lambda expressions and stream objects and stream operations. Okay, so let's start with the collections now. So what is a collection? Collection is just a general interface for a data structure that holds other objects, right? And it's an object which holds references to other objects. So like usually collections contain some references to other objects, and they basically represents this is a relationship, like the composition relationship, like one-to-many relationship between objects, right? So and we've been already working with a lot of concrete instances of collection, like ArrayList before. We're going to look into other possible implementations of the collection interface and see a couple of examples of using those interfaces, the implementations of these collection interface in this lecture. So in particular, we'll look into the 4 different types of collections. We'll talk about lists as usual. So what is a list, right? It's just an interface, and it contains a bunch of methods that allow you to manage objects, okay, within a single object. Also talk about a set. So the set is a collection where there's no duplicates allowed. In lists you can have duplicates, but in sets you don't have. And we also talk about maps. And map is not something that is derived from collection interface, but it is something that can map like keys to values, and keys and values could be two different types of objects. The only restriction that map puts on the collection of objects is that the keys cannot be duplicate, but the values can be duplicates. So, and the other one is some basic data structures that you know, like queues and stacks. And we'll look into the way how those data structures are implemented. I mean, not implemented, but represented in the Java library. Okay, very quickly, we'll go through those examples. Okay, so first of all, before we go and hit the collections, I'd like to explain you something that is necessary for working with the collections. Okay, so imagine that you want to store a collection of integers, right? So integers, as we know, they are primitive data types in Java, right? They are stored in a particular memory block. For example, if it's an integer, it is going to occupy 4 bytes or 32 bits of your memory, and then a variable is basically a reference to that particular memory location, right? So and same goes for other primitive data types like double. Okay, so the double, we know that it's a 64-bit floating point notation, and float is 32-bit floating point notation. Integer, as you know, is a 2C, like a 2's complement notation. with 32 bits size. Long is bigger than that. It's 64. Short is 16-bit integer, right? So all of these different data types, they occupy a certain memory space, and they are the primitive ones. They are represented as values in Java, right? But we know that most of our data structures, like linked lists or even the array list and other data structures, they are based on the notion of references, right? So they contain the references to those values. Okay, so how can we go and make a reference to a particular value, right? So in C++ or in languages like C or C++, this kind of problems could be easily overridden by the notion of pointers, right? So you can point to a particular memory address and then contain a reference. Even if it's a value, you can contain a reference to that value, right? But in Java, we know that we don't have the idea of pointers, and the Java kind of made it clear that, okay, all the primitive values are kind of stored as values, but objects are something that is stored as references. So every time when we declare a variable, for a particular object, particular type, we're not storing a reference to the memory location of that entire object, but we're just storing a reference to that particular object. And then this reference can be used to, let's say, traverse the internal structure of that particular object. So, and we can use this idea of references to build different types of data structures and the point and make a lot of operations that are involved with the data structures, like inserting or removing elements from or finding the elements from those data structures, right? So, but the point is, okay, how we're going to make references to primitive data types. Like in Java, everything is like the primitive data types are stored as values. So in order to overcome this particular issue, the Java API provides you, the Java language provides you with the notion of type wrappers or classes, like the object representation of those primitive data types, right? So if you go and declare a particular value, it's a Boolean, with a capital letter like B, Boolean, or if you declare a particular integer with a capital letter integer, then what you're doing is you're trying to represent those primitive data types as objects. And because we know that objects are stored as references in Java, we can now go and use these objects to create particular collections, particular data structures, which use references to implement the logic behind this particular data structure. Okay, so for each particular primitive data type, we have an object representation of such primitive data type, and these primitive data types, which are represented as objects, are called type wrapper classes. Right? So so each of these numeric type wrappers, like let's say the byte and this one, they can be also grouped into aggregating, class called the number, right? So the number is, as we know, we cannot have a primitive data type which can inherit from another primitive data type, right? So we don't have this kind of notion of inheritance and notion of polymorphism for primitive data types, because these are just values, right? But because we represent these primitive data types in terms of classes, now we can go and generalize these classes into something into something that can be kind of an abstract and can be used as to reference these kind of numbers from like polymorphically. Okay, so we have this kind of general class which represents these type wrapper classes, the numeric type wrapper classes, and it's called a number, right? So if we don't know which particular primitive data type this particular variable represents, we can easily go and define this particular variable as a number and use this particular class abstract type for any numeric value to be stored, right? So primitive data types do not have methods. They are not objects, right? They don't have any internal state. They don't have any particular behavior. They are just values. But the type wrappers, because they are objects, they have their internal state, and they are also they have certain methods that can be used to do certain operations with these particular objects. Right. The only one more thing that you need to know about these type wrapper classes, that these type wrapper classes are also final classes, which means that you cannot create child classes out of them. And the reason for that is because in Java, the child class can replace the parent class, and it can cause kind of some security issues if you, for example, have like an integer class, and its integer class can be extended to something else, let's say my integer class, and then if you go and override some of its property methods that do the arithmetics, for example, and then you replace this integer class with your own integer class, then the entire program, which is kind of doing these arithmetic operations, could go wrong, right? So in order to prevent such problems and not allow the developers to interfere with these basic arithmetic operations, the Java library made these type wrapper classes as final classes, and they cannot be extended to some child class. So you don't have to reinvent your own wheel by just building out your own data structures, because you just need to go and check the Java framework and find out if there is a particular interface for the data structure that you're looking for. And then once you find that particular interface, you can go and re-implement this whole interface for yourself, or you can use the standard implementation of those interfaces for your particular application needs. Okay, so the idea of converting the primitive data types into type wrapper instances and vice versa is referred as boxing and unboxing. So the boxing conversion is a conversion which converts a primitive type to an object representation of that particular primitive type, and unboxing is the reverse procedure. In Java, this actually is done implicitly, so you don't have to do it explicitly by passing a particular primitive value to a represented type wrapper class. You can do it implicitly. For example, here what's happening is you're declaring an array of type wrapper integers, with the size of 5, and then you're setting the first element of this particular array to 10. And remember, this 10 is a literal, and we know that in Java literals are represented as integer as 32-bit integers. Okay, so this is 32-bit integers, a primitive value, and this primitive value is now being, because we declared an array for an integer class, integer object. Okay, this particular primitive value gets translated into, it gets automatically boxed into an integer object, because it's storing, this array is storing integer objects, not integer primitives, right? So, and the same goes in a different direction. So this particular array contains integer objects, but if you want to get some value from this integer object into some primitive variable, let's say int value, then the process of auto unboxing actually happens here without any particular logic to be implemented. So Java can go in both directions automatically without you doing any particular additional operation to convert your primitive data types into the objects, and objects back into primitive data types. If you're using the corresponding type wrapper, Java can go and do it automatically, can cast all that stuff automatically for you. Okay, so we know that the collections, they contain, most of the collection interface contain some interfaces for some methods like adding or clearing the values, also comparing the values inside the object. So how can you go and compare one object in the collection to another object? So all these kind of ideas can be implemented into a particular data structure. And again, collection is just a general interface which involves those methods, and those methods can be then implemented depending on which data structure you're trying to implement. Okay, so collection also provides a method that returns a particular type of an object called an iterator. An iterator is something like, we'll talk about the iterator when we come to the point, but iterator is, you can go and find this iterator design pattern as well, is just an element of the collection. Okay, so it is a little bit of a broader sense element of what we know as the element of let's say a linked list. So if you have an idea about what is linked list, you know that in a linked list you have a node, have an element of a linked list, but if it's a singular linked list, then this linked list element contains a value, and also it contains a reference to the next element, right? So and this, let's say, reference is something that is kind of stored as something in the memory. But for the iterator, it is a little bit of a generalization of that node, where the iterator object knows the value that it holds, but it also can go and provide you a method called next, which determines, okay, like maybe computationally, maybe just going and taking it from some private variable, the reference to the next value. So using this particular idea of an iterator, you can traverse through the elements, you can walk through the elements of your collection in any way you want. Okay, so you can design the logic for the iterator, and you can decide how you'd like to travel through your elements. Okay, so do you want to travel by the index? Do you want to travel like in an ascending order, but by the value, for example? Or again, you decide how you would like to go through the elements of your object, how you're going to iterate through the object, okay, by implementing an iterator class, iterator interface, okay? So iterator object interface. And collection normally provides such an iterator. For each collection, you might go and generate an iterator which knows how to walk through the collection in the process, right? So the collections in a plural form is a helper class which helps you, which provides you a bunch of static methods for searching and sorting or doing some other operations on the collections as well. So let's say if you want to do the binary search, okay, you don't have to go and implement the binary search. Although you know the logic, you can simply go and kind of refer to the binary search method inside the collections in a plural form class, and then use that particular method to find a particular element in the collection. Okay, so so let's go and find look into the first collection. We know that the lists are very simple types of collection. The only thing that the list actually requires you is it wants to have the elements to be like stored in some sort of not stored, but maybe accessed in a certain sequence, in an ordered way, right? So they have to be kind of arranged in a certain sequence. So which means that like one element should be followed by another element, like not like by two elements or three elements, but it always has to be one element after another element, and so forth. So and in the list, if you determine this kind of order for your elements, okay, then you basically have this idea of this notion of list, where you can see your elements in a particular order, and then you have a, let's say, logic of traveling through these elements, okay, in this particular order, right? So the list normally kind of indexed by like arrays, like they're indexed by by 0 as usual, and they can be, let's say, you can go and add elements to the list, or you can go and remove elements from the list. You can manipulate the list, okay, or you can get a specific object called a list iterator to iterate through the elements of the list, right? So there are multiple different implementations of the list provided by the Java library, standard library, and the one that we've been using so far was the array list. And we also have the linked list and the vector. And the array list and the linked list, they have their trade-offs in terms of their performance and the way how they are implemented. The vector and the array list is something that are very similar, but the vector is synchronized, and we'll talk about that when we discuss about the vector. Okay, auto-boxing occurs every time you add a primitive data type to a list of integer objects. Okay, so one more thing that you need to know is that, again, as I said before, and I'm repeating it again, all your collection interfaces, they deal with object representation of primitive types. Okay, they cannot deal with value representation of the types because the values cannot be stored as references in Java. Okay, objects can be stored as references, and most of the data structures that we know, they use the idea of references, and that's the reason we like array lists and linked lists. They are types of data structures which are dependent on the references, and that's the reason we need these kind of type wrappers as the elements of such collections in order to implement such data structures in Java. Okay, so array lists and vectors are resizable array implementations of a list. Okay, and inserting an element between existing elements inside array list and vector is inefficient. Okay, so let me just go and explain that a little bit conceptually, why it's inefficient, right? So we have we got an array list here, and the array list stores. Okay, first of all, let's go and compare the array with the array list. What's the difference between array and the array list? Okay, so in an array we store primitive values like integers and like booleans and so forth. So this is, let's say, contiguous block of memory, let's say, right? And and then let's say this is an array of integers, right? So if integer is 32 bits or 4 bytes, so every block is 4 bytes here, right? And it's going to occupy one big contiguous block in your memory, in your RAM, let's say, right? So, and no matter if it's filled or not, it's depending on the size, it's going to go and occupy 4 bytes, 4 bytes, 4 bytes, and so forth. Like for each particular value, it's going to get 4 bytes, right? Because it's let's say the integer, right? So this array is some sort of an integer array, right? Right. So this is how it's going to store the values. Okay, these are the values. For example, it could be 32, and it could be 16, and so forth. Right. So whenever you go and say integer 0, okay, for example, a is the integer. If you go and say a, this is going to represent a0, right? And this is going to represent a1. A1 is just some number right here, and so it's an integer. Okay, the array list. So we know array lists are array list, and you can go and say integer, and let's say it is b. Right. So this integer array list integer doesn't store primitive types, but it stores object the object representation of the integer, right? So here again you have a contiguous memory block, and now the size of this block is not necessarily 4 bytes. Let's say if you're using a 64-bit computer, this means that this determines the address range, okay, of your RAM. So this could be a 64-bit address, or so another way. Let me just erase that. So 64-bit is what? It's 8 bytes, right? So it's 8 bytes. So we can go and again, if your address range, your RAM's address range is 64-bit, so you can go and say, I'm just storing the address of the memory cell, which contains, let's say, B0. And this could be 4B. And this could contain 32. And this could be some, I don't know, hexadecimal number which represents the address, right? And again, another 8B, another 8B. Again, it could be different depending on whichever system you're using, the way how you define the address in your memory. But you know that in this particular values, you're storing the memory addresses of the objects, okay? This particular integer represents. So it could be 32-bit, I don't know, 64, 16, I don't know, also 4 bytes. And this could represent B1 and so forth. Okay? So the array list doesn't care, okay, if it's storing an integer, it's storing a customer, or it's storing something else. All it knows that it basically needs to go and store the reference to that particular object. And the reference is basically some memory address which points to the location where that particular object is stored, okay? And then you know how to go and traverse through the object's internal structure to get its internal values. In this case, it's integer and it contains just one value, and that's why it's that maybe 4 bytes, which contains this just single number. Okay, so the point here is, like, you're storing the references, but you're storing them in a contiguous block. Okay, like you store the things in the array, but in the array you store values. Here you're storing the addresses in a contiguous block, right? So this is the array list, right? And you can add and remove values into this contiguous block. The Java knows how to resize the block, okay, if it's kind of it's exceeding the initial size and so forth. So it knows all that stuff because it knows the size of everything. And the point is, this is how actually goes and implements this array list. Okay, we also have a different implementation, right? So you know it from the data structures class. We got a linked list, and in the linked list you have some header which points to, so you know the beginning of you store some information about the beginning of your linked list, and then you have some values. You have some values. So this could be a linked list, again, integer. And let's say it's C, right? So now this might represent, again, it could be 32 here, and then the reference, then the memory address, right? So I don't know, it could be 4 bytes here and 8 bytes here, and this is also 8 bytes if you're using like 64-bit for defining the addresses in your system. And this is what? This is just the value, right? So, and this is the first value, and this is the second value. It could be 16 and another, and so forth, right? Until you go and find the latest element in your this one. Okay, good. So and you know from your data structure class, right? So inserting into array and array list is it's a linear complexity. So you have to shift all your elements in this direction if you want to insert something in between. Okay, but so it's a complex operation. But in linked list, it's easy operation. All you need to do is 2 operations. You break. You point the element to the new element, and then you point the new element's reference to this one. So there are 2 operations. So it's a constant operation. This is the linear operation. This is the constant operation. So this is harder to do the insertions and removals in array list, but it is easy in the linked list. But indexing elements, finding the elements in array list is easy because it's just a one constant operation, arithmetic operation. In linked list, it's a linear operation. So if you would like to find I don't know, C12, then you have to go through all the elements and then find the element here. In array list, it's easy. You can go and point to the second 12th index and then go to the memory location wherever it is pointing. So you can go and talk about these kind of trade-offs between the linked list and the array list, and whichever one is good for you. If you're reading values a lot but not doing a lot of modifications, then it's an array list. If you're doing a lot of modifications rather than reading, then it is kind of the linked list that you would like to choose. The array list and linked list, so the array list has a one particular version called the vector, okay, in Java, and let's call it integer as well, and let's call it D. So the vector implements exactly the same thing as array list, but along with that, it also implements the something called, I don't know if you heard about that, the locking principle or semaphore, something called a semaphore, or I would rather say not semaphore but monitor, because it implements itself within this one. So I had made a mistake, so let me go and remove this guy. It's not a semaphore, to be more precise. It implements the concurrency pattern called monitor. Monitor. So what is monitor? Monitor is a data structure which takes care of its locks. Okay, semaphore is just a separate object which can determine if the object is locked or not locked. But if the data structure encapsulates the lock into itself, then it becomes a monitor. So it knows, okay, when someone is accessing reading the value or writing something into the value, it knows that, and it can tell the other threads trying to access the vector, okay, about that. It can block the other threads if some thread is doing some operation with this array list. Let's say it's reading some value from it or writing something to it, okay. It can block the other threads from accessing or from modifying this particular list while the first thread is doing its job, okay. So it can prevent the problems of like phantom read and then dirty write, okay. So the problems of concurrency when you have multiple threads. Again, we'll talk about the problems of concurrency again maybe in the next lecture. But the point is, if you're familiar with the problems of concurrency, vector data structure implements exactly the same way, is implemented exactly the same as array list, but it also knows it can monitor its locks. It can prevent other threads from using the data while one thread is accessing it. Okay, it implements in other words, it implements the methods of mutual exclusion. So you can go and call it like this as well. So threads are mutually exclusive. One thread can access while others wait, and one thread releases this particular data structure, the other can go and access it, so forth. So the vector is kind of a thread safe a version of the array list. Okay. So I hope it is kind of clear what vector is. So yeah. So we talked about the efficiency, we talked about the synchronization part, yes. So linked lists can be used to create, as we know, the linked lists can be used to create other data structures or advanced data structures like stacks, queues, and decks. Okay, so the deck is a two-sided queue, right? So and again, I'm not going to talk about the way how you can go and implement a queue or stack. Again, it's outside the scope of this particular class. But and Java actually provides you all these implementations outside the box. You don't have to go and do this. And there are certain methods that you can use for a list. Let's say add, get, size, getting number of elements inside a list. Or iterator method, which gives you the iterator for that particular collection. So iterator is what? As I said, iterator is some sort of a class. So let me go and draw that class. So iterator is just a node. So iterator class, iterator. So iterator class contains value which it holds. It can be any type, right? It could be an integer, it could be customer, but along with this it contains a method called next, right? And again, this next can be, okay, you can go and implement the next element. You can choose, you can find any logic for that particular next. So it is just a function. It is open-ended, okay? It's not necessarily you go and if it's a linked list, for example, you can go and store the next object here as a reference, right? And then you just say return just next object, right? And next object is just another iterator, okay? It is not a value again, it's just another iterator. So, and which basically has the same interface, and again has the same next method and so forth. It could be implemented like this, or it could be, again, you might decide not to store it. Let's say kind of you're implementing an iterator, dynamic iterator, let's say. So the next is something, some logic which let's say manipulates the value that you have already. For example, you can have an iterator for the squares of 2. Sorry, for the powers of 2. Right? So you want to have an iterator for powers of 2. Can you go and do this? Yes, of course. You don't have to go and calculate, let's say, 10,000 instances of it. Okay, you can store the value is equal to I don't know, 2 first, and the next is equal to what? The next method is equal to. So you say return. Right? So return is what? So you just go and increase the current degree of power, right? So you say value, and the power is, let's say, n plus 1 or whatever. N is equal to whatever, and then you just return it like this. Or maybe you say, no, you don't do it this way. Yeah, you just create an iterator object, and you set the n to n plus 1, and then return that new iterator. Okay, so you can go and create a dynamic iterator like this, which is not like traversing something that is already stored in the memory. It simply knows how to calculate the next value, right? So these dynamic iterators, sometimes called generators, okay? So these dynamic iterators are sometimes called generators, and you can go and create a generator out of it like this. So it's not traversing some values from the memory, but it's doing the computation to the next element and so forth. And you can use this iterator class again to iterate through your any for loop or anything. So again, look into this particular next method and see something a little bit broader than that. Okay, it's not just storing a reference to a particular next element. It could be something computational as well. Okay, if it's something computational, then this iterator is in fact is referred as sometimes in some programming languages called a generator. Not an iterator, but generator, because it generates the next value. Okay, good. So let's continue. Yeah, and iterator has a next method. As you can see, iterator has a remove method. Basically, it removes this particular element from the list. And okay, so you can go and implement all these methods, and those methods are also the has next method will peek, tell you if there is a next element or not, and all these methods can be used again to walk through all the elements here. So this is one example of an iterator. So you got a collection. This collection is let's say string collection, right? And this collection again again, the collection is a very abstract interface. It could be a linked list, it could be an array list, doesn't matter. Collection has this iterator method, and this iterator method gives you something that you can use to iterate through the elements, again, without knowing how those elements are accessed, okay, in which order they've been accessed. All you need to know is just the next element until you don't have any more elements left. Okay, so this can be just one example of going through this one. Okay, so I'm not going through all these linked list methods. You just can go and read out all these different methods that list provides you. You can go and do some bulk adds, for example, right? So adding elements element-wise or add all will take another list, okay, and then adds all the elements of this particular list to this list, and so forth. So you can do some bulk adds, you can get their iterators and work with these examples, okay? So these are, again, you can add to a particular location, add last, add first, okay, or to a position. Let's say you would like to add it to the third index, this particular value. So all these methods are quite self-explanatory. Please go through these examples yourself. I'm pretty sure you guys will figure out what do they mean. Okay, another data structure that is available is a priority queue. So you know what is a priority queue? It picks you, it adds the elements in a random order, but it pops the elements, okay, from the queue. Dequeues the elements from the queue depending on their corresponding value, corresponding priority. Okay, so the poll is something that you can use to remove the highest priority element. Pick is something to get a reference to the highest priority element. Offer is the element which puts inserts the element into the priority queue. Clear and size, as you know, they just removed all this stuff. So you're going to go and use this implementation of the priority queue. Okay, you can just say new priority queue and the corresponding reference types that you would like to store in that priority queue, including the type wrappers for primitive data types. Okay, and the sets are collections where there's no duplicate can be possible, and there can be a lot of different implementation of sets. Okay, the hash set and the tree set is one such implementation. Okay, so hash set, as you know, uses the hashing algorithms, hashing methods to figure out if there is any set in this element or not, if there is any collision or not. If there's no collision, it goes and adds. If there is a collision, it doesn't go and add the element it does into the collection. So, and it's a very fast, extremely fast technique for implementing hash sets using hashing functions. And the tree set implements it using this the binary tree. Okay, so a tree-based implementation of a set. Okay, so again, you guys know how to do the implementation for the sets. There are two different implementations. You can go and use all that stuff. And if you need to store a unique set of values, okay, then you probably have to. Okay, this one. Okay, what if your data set? What if your objects are not type wrapped objects like strings or integers, right? Let's say it's customers and you'd like to store a unique set of customers. Then what you need to do is you need to go and override the equals method. So you know that every object has the equals method, which is implemented by the parent class called object, by the superclass object. So equals has a default implementation. It simply compares the references for the objects. If the references are different, then these two objects are not equal. If the references are the same, then these two objects are the same. Okay, but for customers, it might not be the case. Sometimes you would like to check the customer by their maybe email address, maybe by their ID or by their passport number, even if these are two different objects. Okay, but they could be representing the same customer. So you can go and override the equals method, okay, and override it, and then compare their properties, okay, their password property, whatever. And if it is equal, then you can just return true, or if it's not equal, then you say false. And once you go and override this particular equals method for a particular class, and then you pass this particular classes to hash set, the hash set can go and kind of figure this out. for you. Okay. Okay, good. So no, not the hash set. Sorry, the tree set. Tree set can go and figure this out for you. Okay, so if you do it with a tree set, because tree set kind of checks if it's equal or not. It basically uses the comparator as well to figure this out. The hash set. You need to read the documentation if it's doing that as well or not. Okay, good. So so you can go and say create sorted sets as well. Sorted sets, they add the elements. They prevent the duplicate elements, but they can return you the elements. Okay, in an ordered way from the set. So it is the extension of the tree set, and can be gone and implemented this way. Maps are not child classes for are not derived from the collection class, but they are also can be regarded as collection. What they do is they do mapping of two object sets. Okay, and the way how the mapping is done in Java is they do the many-to-one mapping. Okay, so there's the keys cannot be duplicates, but the values can be duplicate. Okay, so if your map contains both unique keys and unique values, you can call it as like a one-to-one mapping. Okay, so hash tables, hash map, and tree maps are just an implementation of the maps using different techniques. Again, hashing techniques and the tree map techniques. Again, you can discuss about the certain aspects of such maps. Okay, again, in the data structure class. The one thing that you need to know about maps, like with the hash maps, is something called the load factor. So the load factor is the number of cells occupied divided by the number of cells available. For example, for your hash map, you are allocating 10 cells, and then your hash function kind of distributes the values into let's say 5 cells. So you have 50% load factor. So the higher is the load factor, the greater is the chance of collisions. And you know what is a collision? If your hash function allocates the same element, allocates an element to a cell which is already occupied, okay, by some other element, and that is kind of a collision. And if this kind of collisions happen, okay, then the performance of let's say reading and storing values into your into your hash set becomes deteriorated. Okay, so this is kind of a trade-off. What you want execution time performance, or you want memory space optimization. If you want faster read and write operations, then you have to sacrifice the memory. But if you want to save the memory, then you have to sacrifice the execution time for read and write operations. Okay, if you're using this like hash maps and this one. For the tree maps, it is kind of logarithmic. Okay, so it is you don't have to make this kind of trade-offs in the tree maps, right? Okay, good. So these are just some examples. Again, I want you to walk through these examples too in your own pace. Okay, so these are some examples. And synchronized wrappers, they make all of the connections, including the array list and this one, sync locked. So although we have this vector data structure for thread safe lists, okay, we can actually convert all the data structures, including sets and maps and lists and everything, into a synchronized list or synchronized sets, and make them thread safe. Okay, so what is a synchronized set? It is just a wrapper class. It is a class around the existing implementation of a set. So what it does is it acquires the lock for that particular resource, and then delegates all the operations to the inner data structure. Let's say if it's a synchronized set, then it encapsulates within itself some implementation of a set, let's say hash set, okay, and then just simply if you would like to add something to this hash set, then it just acquires the lock and then adds the element and then releases the lock and something like that. So it basically wraps all the operations of the sets with a particular thread safe logic, and this way you can if your set is being accessed by multiple threads, then you can go and get the sync safe or thread safe implementation of these data sets by calling the synchronized set method of the collections helper class. So the collections API has this synchronized list, and then you pass the existing list into this one, and you'll get the wrapped a new list with his thread safe. So you can convert any data structure into thread safe data structure like this, okay, without just going and creating a vector or something. Okay, so certain so if the two threads try to access the same thing at the same time, right? So you can go and you can also make things synchronized, but you can also make certain data structures, let's say, immutable, unmodifiable. Okay, so once you want to just create a list and then you don't want any function to modify those structures, you can also create a data structure which prevents it from being, let's say, modified. You can make them read-only. So in order to do this, you can use the collections classes. There's a collections class, right? Collections classes, unmodifiable, okay, set or unmodifiable list methods, and pass the real actual instance of the list or instance of the set, and then get something that is unmodifiable, something that is not cannot be changed. If someone tries to change something, then it will go and return the unsupported operation exception for that particular method. So it will cause an exception, so your values won't get implemented. Okay. Okay. So if you would like to kind of re-implement the whole thing yourself, right? So you want to implement, you have your complete customization of this entire process. You can go and kind of inherit from the abstract collection, abstract list, or abstract map, and all of the methods that are defined inside these abstract classes will be given to you. So you just need to go and override all the implementation. You would like to have your own list, okay? Go and implement abstract sequential list and the way how you're going to access elements, and maybe it will be better in the performance and so forth. And you can use those lists in your programs for better performance. Okay, so Java provides you a set of abstract classes for implementing your own data structures. Like if you want a list or map or set or queue, you can go and implement them yourself too if you want to. Let's say you want some data structure which kind of synchronizes with the database, right? So it gets its values from the database, it adds things into the database. Then perhaps you would like to go and, let's say, create your list which is implementing this abstract sequential list or something. Okay. So now let's talk about the generic methods. Okay, so the methods which contain which could be a template for multiple different data types. Okay, so we're going to talk about like generics, the idea of generics in the first, the idea of the generics. Why do we need generics in the first place, and what does it mean, and like all that stuff. So far we've been using this kind of diamond notations, like this something like this, left and right, right? We haven't get a real understanding about what actually this means. So, for example, I've been saying array list, something like that. I've been using something like that, right? Array list, and then I'm using this diamond notation, this something that is called diamond notation, and I've been using saying integer. And you might have an intuition of what this diamond notation means. This diamond notation is the generic type. Okay, is something that this particular class needs for implementing its operations. So this class needs a certain it does certain operations, but its operations are dealing with certain values, and these values need to belong to a certain type, because Java is a strongly typed language, right? But we don't know those types at the beginning, or we know these types, but we have a lot of duplications. So for example, let's consider this print array method. So we have this print array method, right? So this print array is idea of this implementing this print array method is pretty clear. I mean, you know how to iterate through the array. You got a bunch of arrays here, like array for integers, double, and character. You just need to, you would like to go through all the elements in this array, right? So if you would like to go and implement this method for integer, double, and character, what you need to do is you have to do the method overloading. So you go and create a print array method, and the input is now the array of integers, and you're iterating through integer element here, right? And if you want to do the same thing for double, then you have to duplicate the entire code, but the only data type that you're passing here, it is different. The everything is the same, right? And then you got another method for characters. So basically, these methods, they do exactly the same thing. The only thing that's changing is the type of the input, right? The type of the input. So this is how you've been doing all this job of implementing the same method for multiple different data types. So what if you could go and create some template method, a method without specifying the type of the argument that you would like to deal with, okay? But everything else is exactly the same, right? How good it would be. Of course, you would kind of save a lot of time, again, save yourself from a lot of duplications, okay? So, and this could be actually achieved by creating something like this, right? So what I was talking about is, okay, what if you could go and just leave the type as something that can be specified by the caller, okay? So let the caller specify the type of the input. You just go and create some template method, and this template method has some generic type, which is represented with this T character, okay? So T is not a particular type, it's not a particular class, it is just a variable, not a variable, I wouldn't say it's a variable, it's some symbol which represents any type that you would like to use, okay, inside your particular function, okay? So in this case, this whole overloading, method overloading, can be replaced with something like this. So you declare, so if you need, for running this particular method, if you just need a single type which is unknown and which can be specified by the caller of this method, who is calling the method, it's his responsibility to specify the type for that particular method, okay? Then you can go and declare between, okay, just next to the, just before the return type of the method, you can declare the unknown types, and then you can, I mean, T is just a word, you can go and use any letter here. So you can go and declare such unknown types, and then you can use these unknown types anywhere in your function, okay? Including its signature or including its body, right? Including its head and its body. So you can go and, once you declare this particular unknown type, you can use it anywhere you want. You can even make it as the output of your function too, right? So let me show you that in the next example. In this example, so I have this generics here, and this is the overloaded methods, right? So the overloaded methods, as you can see, I have all these methods here, right? And I can go and replace this thing with a generic method. And this is my generic method. So I can go and replace this T with something else. I can go and say, I mean, if it's a type, then the convention is it's called t, but I can call it t1, no problem, and I can give any name for that. If my function needs, if my function has two unknown types, I can go and say t1, t2, and I can go and say maybe it goes and returns something of a type t2. Okay, that could be the case too. Okay, so so again, I can go and specify different types, unknown types, and then use these unknown types to, let's say, iterate or to do a lot of different things that are relevant to this type. Okay, so now let me go and execute this particular code. So I can go and say set package name to generics. Yeah, sorry. Okay, so let me go and execute that. If I go and execute it, it will work. As you can see, it is iterating through the integers, it's iterating through the doubles, and it's also iterating through the characters. And I just have a single method. And while I'm calling this method, note how I'm calling these methods. I'm just passing an instance of integer array. My print array method is automatically knowing exactly, okay, which data type it is input array. If I'm passing integers, then this t is equal to integer. If I'm passing double, then this t is equal to double, okay? And if I'm passing character, it's equal to the character. This t is equal. The Java automatically knows, right? This whole thing. But in fact, it doesn't even automatically know that. What it does is it does a little bit of a trick here. It simply, whenever I go and write a generic method like this, what Java will do is it will replace this thing into something like this. Okay, the reason is during the runtime, of course, not during the compilation time. So when the Java program is running this particular method, it cannot run methods without concrete strong type references. Okay, Java is a strongly typed language, and every symbol in this code must have its concrete reference. For example, if this input array is stored somewhere as a reference, I need to know its type. Otherwise, I cannot do anything with this particular variable. So I need this kind of constructs to make my code easier. Okay, so to override these kind of problems, right? In the first place. And also, there are certain things like in the class generics. This is a method generics. In the class generics, I can do certain compilation time, syntax checks for methods. Okay, so compilation time syntax checks can also be enforced on the functions. But at the end of the day, these methods will always be converted into something like this. So object, as we know, is just the superclass for all objects in Java. So any like double, integer, anything would work with this method. If I pass just an integer, it would work. Okay? It simply replaces that like this. So you just need to bear this in mind. And this process is called the erasure process. So it's a process called erasure. It erases all the the type specifications with something called, with a superclass called object. Okay, so we have we can also override the generic types as well, right? So this is a print array. Sorry, overload, not override. Overriding is when you're inheriting. So I can go and create another print array. But the only thing that I can do is maybe I want a different let's say set of parameters, right? So I can go and say integer, say count or something like that. Now you can see that these are two different methods, or I can go and say t1, t2, and I can say T1, and here I can say T2. And here I can say, let's say message. I'd rather say message. And I can say println message. So with some header message, I can go and create a print array. And the header message, I don't know, it could be a string or it could be something else. And I could pass, it is integer, right? So I could go and do this. Now this print array method, this one will work, and it will simply just go and print out the message. It will know that this is a string, and it simply goes and prints out the string. Let me go and start that. So it's saying it is integer, and then the integer itself, and the others are not doing anything. This method is getting called. So I can do the method overloading even though I'm specifying the generic type here. Okay, so method overloading is not gone. Okay, the generic classes are another important thing that helps us to create classes which do template operations without knowing with which element they are working with. Okay, so one example of such generic class could be a stack or a queue or any data structure we were working with, like lists, for example, or any collections, right? So that's the reason we've been defining these kind of collections with generic types, right? The reason for that is like these list operations, they are independent of the elements that they are dealing with. Okay, they're not dependent on the elements type exactly. What they are dependent on is maybe the structure of these data of this collection, but they're not dependent on the element itself. So that's the reason we can go and define like array list, and inside the array list, specify the type with which the elements of the type of the elements with which it actually works. So for example, I can go and implement a stack like this. The stack class deals with elements of a type T. Now, okay, within the stack, I can go and create an array list, right? So this is the array-based implementation of a stack, right? So, and here I have a size, right? So I'm defining, I'm setting this, I'm basically calling this particular constructor here, right? If it's a no argument constructor, so, and then defining a new element, array list with a capacity, certain capacity, right? So, and pushing, and I'm enforcing that the value that should be entered into the stack should be a value of type T. Note that I've been defining some unknown type T here. So I'm enforcing this T everywhere, right? And then the return type of this pop method also needs to be T, right? So the values from the stack are coming here. So let me show you the stack here, implementation. So I got the stack implemented as usual. This is my stack. It has T type, and within itself, it is storing all the objects as an array list. It has a size. The size is 10. If it's given is 10, it's not given, then you can go and specify the size. And it has two methods, right? So let me go and make sure that they are coming from the generics package. And this guy is also inside the generics package. Okay, and this guy is also inside generics package. Okay. So empty. Yeah, empty stack. Yeah, it has it. Okay, so yeah, let me go and make sure that this guy is also inside generics. Forgot to include this package. Okay. Yeah, we have it. And it's been used. Everything is cool. Yeah, why it's causing the problem? Okay, so anyway, hopefully it should work. So we have basic implementation of a stack. Note that I'm enforcing this types, whichever type that I asked. Okay, so who is going to tell me, which type of elements this stack is manipulating? Of course, the one which is using the code which is using this stack, the client code that is using this stack class is going to specify the type for that. Okay, so how do I specify that? I specify like this. I say stack double, and I got a double stack, right? So I got this double stack. Okay, so and so here I got. I mean, I can go and say double stack, and I can say push. And note that my IDE is now asking for a double, right? Not asking for a T, but it is asking for some double, because this double stack has been created with this particular specific type, right? If I go and try something else, let's say a string, it is going to give me a compilation error. This is a compilation error. And it can prevent me from, again, if I've been using objects all over, I wouldn't have any, okay, instead of this template types, right, generic types, I've been using, instead of, if I define the stack and elements of the stack as objects, like everywhere, right, this takes an object, and this returns an object. I could have defined a stack without this generic type here. I could say my stack just simply deals with the object class. Then this wouldn't cause me a compilation error, right? Because object is just a string, object is this one. But because I specifically said the stack is for this type of elements here, right? Double. Now I can have this kind of compilation errors in my code, and this one can be kind of prevented. This kind of problems can be prevented in the future. I can enforce the client to use a only single type, whichever type it specified at the beginning while declaring this variable, and use this one. Okay, so this is something that is important when you're defining classes with a generic type, right? Okay, good. So you can go and play with this stack as later on. The code is given to you. I'm not going and explaining everything here. Okay, so the raw types are the types where like stack is something that contains a generic type. But what if you do not specify this generic type? What happens? Then it's not a compilation error. It is simply, okay, it goes and replaces this T. Java will simply go and replace this T with the superclass object. So it will be the array list of objects, and this push will be object, the value object, and the pop will return an object. So, and you will be simply dealing with the raw type, okay, the raw elements, and it will work as well. Okay, so if you don't know which kind of stack you need, you can go and use that kind of without specifying the generic type as well. But once you go and create a class with a generic type, then when you are using this class in your client code, it is better you go and specify the type for that particular class. Okay? To make sure that the backward compatibility. Okay, now we finally reached the second half of the lecture. It is so in this lecture, in this part of the lecture, we will discuss about how we can go and define our tasks using a different paradigm, not the imperative paradigm we've been using so far in Java, but we can also get the benefits of interpreting our programs using a slightly different paradigm, using the function-oriented programming paradigm, functional programming paradigm. So in this particular half of the lecture, we'll discuss about what is functional programming, okay, how it complements our object-oriented programming, and how Java actually interprets functional programming in its syntax, okay, what are the Lambda expressions, okay, and how they implement the functional interfaces, some of the functional interfaces. And we'll also see a couple of examples using this the objects which are represented as streams, and a particular type of objects like IntStreams and custom streams for any type of the object, right? So so prior to the Java version standard 8, Java actually supported 3 different programming paradigms. So the first one, as you know, it's a procedural programming, it's imperative paradigm. And we also, Java, since its beginning, it actually supported the object-oriented programming paradigm. And now it also supported the generic programming, the one that we covered in the first half of the lecture, being able to specify generic types. And now, after the Java Standard 8, we have a new programming paradigm being incorporated into the language. It's called the functional programming paradigm. It's a new language with its own capabilities, and it's own some sort of a syntax in representing our programs. So what is the difference, right? So what kind of new things that this functional programming brings onto the table, right? Before functional programming, if we had some sort of a data, right? Let's say like we have the data set in terms, it is represented in the form of an array, and we'd like to do some like data processing, right? We'd like to go and, let's say we got an array of integers, we'd like to find the square for these arrays of integers, right? So in order to do so, what we would do is we would go and write some for loop. We have to iterate every element of this collection, do certain tasks, and most of these tasks can be done again sequentially. Let's say find the square of each element, right? And then add these newly created element into some other array, and then return a new array with array list with all these squared elements. So this would be kind of our way of dealing with certain data processing, right? So in a sequential way, in a way we specifically determine the way how we're going to iterate through each element. We specifically determine what sort of operations should be accomplished in a particular steps, right? And also we need a separate, let's say, array for storing the results. So we need some mutable variables for storing the intermediate results of our computation. And at the end, we are going to return that intermediate results. I mean, which are filled with the squared, for example, integers as a result. So we need a lot of we have to specify a lot of important things, important aspects of how this particular job is done, right? So I mean, it might sound natural to you, like you're just doing things in a step-by-step manner, but if you just pay attention a little bit, what you really want is you just want, okay, you have just some data set, and what you want is just another data set with squared values, with squared elements, right? And everything that is inside, okay, like is just like that's happening inside the loop, and the way how you're iterating through this is not relevant. Okay, so this is what you really want. Okay, so you want to translate, you want to transform one particular data set into another data set, and it is not necessarily a sequential procedure as well. So in a functional programming paradigm, instead of specifying the steps that we need to accomplish one by one, including the iteration of elements as well, we simply specify the task that we'd like to accomplish, right? We'd like to tell what we want at the end, or what is our kind of imagined output, and let the programming language decide how it's better to go and implement that particular functionality. Okay, so it's kind of a declarative way of writing things. Okay, so you give the initial state, you give what kind of features, let's say what kind of properties you want from that, what kind of transformations you want to apply to this particular data set, and then you specify what you want at the end, right? And let the environment, the compiler, decide how to implement that particular functionality for you. Maybe how to iterate through the elements, or how to calculate those things that you need. Okay, so all of these things are not necessary. These things are not important for the sake of the task's completion. All you need to know is just need to specify clearly what you want from this data set, right? You don't specify how you're going to accomplish it. You just say what you want. What is your final objective? You just need to describe that final objective, final output, and let the program do the job, right? So you're basically asking the environment, the compiler, to do the computation for you, instead of telling the computer one by one what needs to be done. Okay, so this is kind of this way of writing programs actually gave rise to the functional programming paradigm, where we focus on the task itself rather than the way how this task should be accomplished. Okay, so in particular, we will kind of abstract out this notion of data at all. We say, okay, you know what, a program is independent of data. Okay, yeah, data is just some sort of an input, and a program needs to process this data and output something to that, and everything that is stored inside this program is just a means. Okay, it's not the end. It's just some intermediate things that are happening within our program, and when we do our imperative programming steps in a purely functional programming languages, what we need to take into account is the immutability of the data source. Okay, being able to disregard the data from our computation. Assume that the data is something that can be abstracted out. The way how you store the data, the way how you get the data, or how you save the data, how you read the data, and how you store it someplace, or in which particular structure you're going to, let's say, access the data. It is not important. Okay, it's not important at all. What is more important is what operations you're going to do on that data. Okay, and take the example of some algebraic expression example, and another example, like some function, right? When you're defining a function, let's say the quadratic function or something, you don't care about the data. You worry about the function itself, and then when you're analyzing or dealing with this particular function, you can simply represent this function and tell what sort of operations this function does, but it doesn't matter what sort of data it deals with. Okay, so it takes the data, it does something to the data, and then spits it out to some other function. And the other function catches up the output and does something again to that data, and so forth. It hands it over to another function, and so forth. What you can do is you can basically build some chain of functions that transform your data in a particular way, and then give you the data in the shape that you would like to have it, right? So, and without going into the idea of variables. Okay, so you don't need the idea of variables at all when you're dealing with a functional programming language. You need just the symbols to represent the operations that you would like to have, but the variables, the mutable states, the variables are sometimes called the mutable states. These mutable states, the places which you require a memory and the storage, are disregarded from this whole the paradigm, and being able to exclusively interpret the tasks in terms of functions and in terms of the operations that are involved in processing this data. Okay, so functional programming focuses on immutability, not modifying the data source, and being processed or any other program state. So no modification of the programming state, no introduction of variables at all in our program, and dealing with the program, dealing with the data as if it flows through some pipeline. Okay, so we specify some sort of a pipeline through which our data should flow. Okay, and in the pipeline we specify what sort of transformations it has to go through, and at the end of the pipeline we'll get the data what we want, okay, in a shape that we want. Okay, so Java functional interfaces in Java are, I mean, again, we know that the Java is purely object-oriented programming language, and even if it's incorporating a new paradigm, I mean, Java is incorporating a new paradigm into its own language, it has to go and create certain, let's say, certain interfaces that help you to interpret the constructs that are known in the functional programming, and for that, Java goes and introduces you some like single abstract methods. Okay, the functional interfaces with some shape, let's say, right, with some method, and these functional interfaces can be used to determine the operations that we are going to impose on the data. Okay, and then describe our task that should specify how we're going to translate our data into the data that we'd like to have. Okay, so and then we have some generic customizations, and we're going to talk about this single abstract method. So basically, in Java util function interface, we have 6 basic functional interfaces. These are nothing but interfaces with a generic type, and they have a particular form, right? So one interface is called a binary operator interface, and this binary operator interface is an interface. Again, any functional interface is just an interface with a single unimplemented function, right? So we have only one function inside that interface. That's called a functional interface, right? So let me go and write down that for you. So the binary operator interface is a functional interface, which means it has this apply method, only one method, which takes 2 arguments of a type t and returns a value of a type t. So we're talking about some operation like addition, multiplication could be, or logical operations, any binary operation which take 2 operands and return some value, right? So you can imagine how this particular interface is defined in Java. So you can say, okay, this is an interface, let's say a binary operator with a generic type t, okay, and it's an interface, interface, and it has just a single method, and it's called apply, and it takes 2 arguments of a type t. Yeah, it returns a value of a type t, and it takes 2 values, 2 arguments, value 1 and value 2, okay, as an argument. So it returns also t. So if you would like to describe an operation which involves 2 operands and then returns the same thing, then you might go and implement that interface and then specify what this apply actually means for you, what sort of binary operation you're actually introducing into your functional programming language. Okay, again, when you're implementing the apply method, of course you're going to use the procedure-oriented programming, and you're going to do all the operations that you want to do. But the point is, like this particular functional unit, it is a functional unit. It does something. Okay, it takes 2 inputs and produces the output, and then you're going to use this as a building block to define your task. Okay, the task that does something really specific. Another type of functional interface, SAM, okay, these are SAMs, let me call them SAMs, single abstract methods, okay, this SAM, another type of SAM, is consumer, and the consumer, as the name suggests, accepts a value of a type T but doesn't produce anything, okay? And it has a method called accept, right? So it takes a value of a type argument T but returns void, okay? Returns void. It doesn't produce anything. It just takes some value and that's it. It doesn't produce anything else. Okay, so I can go and write down the interface, how it's defined. Okay, in Java, you can go and assume that it's consumer of a type T, and it has a method called void method called accept. Yeah, and it accepts something with a type T, some argument. Okay, or only single argument. Okay, not many arguments. So it takes one single argument of a type T and doesn't produce anything. That's called the consumer. We also have a functional interface called function, SAM called function. What is function? Function has a single method which takes a single argument, not two arguments, a single argument of a type T and returns a value of a type R. R and T could be the same or they could be different too. For example, it has an apply method, right? So let me go and specify that one as well. So interface. So this interface function. Now it has two generic types, T and R, right? It has two generic types. It has a single method called apply, which returns R, something within R type, and takes an argument of T. So if you want to do some function which, let's say, maps the input from one space to another space, okay, you can go and define some function like this and then use it as a kind of building block in specifying your tasks. And we're going to talk about how you're going to specify the task using a function programming paradigm. You also have a predicate. Predicate is, again, specific type of function. In fact, anything here other than this binary operator, because it has two arguments here. It has two arguments. Function has just single argument. Consumer is a specific type of a function. It returns void. Predicate is a specific type of a function. It takes something with an argument. It has a test method. Say one single argument with an argument with a type T, but now it returns Boolean. We know what is the output for that particular predicate. So I'm not going to write this down. I think you already got the idea. So it just has a one single argument for type T. It could be an integer, it could be something, but it must return a Boolean type. Okay, it must return a Boolean type. That's called a predicate SAM. And we also have a supplier. Supplier is the opposite of the consumer. It doesn't take any value. It has a get method. Takes no arguments, but it produces a value of a type T. Okay, so this get method doesn't take any arguments, no arguments at all. At the end, it produces some value. So that's why it's called a supplier. It produces something. It could be a random number generator. It could go and get the data from some mutable state, from some variables, from some outside external source, okay, which has not been passed to the function directly. It can go and get the values from the database, from some variable, from some array or anything. It can go and get the data from some mutable source and pass it pass it to someone else. Okay, so some other function which can go and play with that and do some data transformation. And we also have a unary operator. You know, unary operator is just has a get method. It takes no argument. Okay, no argument, but returns a value. Sorry, not no argument. It takes a single argument. So there's a typo here. Single argument, and then returns a value of T. So a unary operator, there is a typo here. So takes a single argument, okay, and returns a single argument, and both should have the same type. So the not, for example, is a unary operator. It takes one Boolean expression and just finds its complement. Okay, so any sort of unary operators you want, you can go and define them by just implementing this functional interface. Okay, so once you go and implement this functional interface, okay, first of all, how are you going to implement these functional interfaces? Okay, of course you can go and implement them in a standard way, like in Java way, right? So for example, you would like to implement a unary operator. What you would do? Okay, so for example, you want to implement a Boolean not. Okay, so what you do, say class, let's say not operator. Okay, and which implements what? Implements, oops, say implements unary operator, and then you specify the type, and you can say Boolean. Okay, and you open it, the braces, parentheses, this one, and now you have an overriding function, something that you need to override, and this function is get function, right? So you're going to say public. Okay, and the type is what? Type is Boolean now. Get another Boolean. So B, let's say, right? And then you could go and say return and B. Okay, so not B, something like that. So so this is one way of like implementing any of these operators that you need. But there is an easier way. Instead of going and writing all this class and implementing all this stuff, you can go and implement these SAMs, okay, using a slightly different syntax. Better, shorter syntax. And this syntax is called a Lambda expression. It's called an anonymous method, and it's a shorthand notation for implementing an entire functional interface, right? And you can store them because these are instant interfaces, and interfaces can be declared as variables, right? You can store them into a variable, and you can use them inside your functional program, okay, of which we're going to talk, okay, later in this lecture. So how are you going to specify, for example, this particular operator using a Lambda expression? So this not operator could be specified as follows. You could specify some variable, or let's say you're going to specify something like x Okay, so this small expression, a Lambda expression, replaces this entire implementation of a unary operator. Now you can look into this. It's a unary operator, right? It takes something of a type x and returns something of the same type, but it does some Boolean operation here, right? So this is This is a Boolean unary operator. It takes one value and it returns another value, okay? And the value, the type of the input and the output is also the same, right? Is exactly the same. So this is a simple Lambda expression, and that's how you can specify this Lambda expression. You can store them inside a variable. So you can say, unary operator, and say, let's say B is equal to x not x. And now B will be an instance of this class, not operator class. You could have said new not operator, and then that doesn't pass anything, or you could have said this entire thing like this. So as you can see, it's a shorthand notation for representing the implementation of these SAMs. Okay, so let's go and look into other different types of Lambda expressions, how we can go and specify them. The general syntax is you open a parenthesis. Sometimes you can skip the parenthesis if you have just a single argument. If you have multiple arguments, you have to use a parenthesis. And then you just write the types, or sometimes you can even skip the type of your parameter. It's also possible because it can be deduced from the operations that you've been using here. Okay, so so you can go and specify the type, or you can skip the type, and this is just a function. Okay, like the function that you define in algebra is a function, and this function is equal to this one. Okay, so it's a function with two inputs, and it's equal to this number. So you can now specify the body of the lambda. So the body of the lambda can be specified with curly braces. But if you have a single line, okay, of code which yields a value, then you can skip the return keyword, and you can skip this curly braces like I did here. I don't have a return keyword. I'm not using the curly braces because this expression already yields a value for me, and it's just a single line expression. Okay, so I can go and skip all that stuff. So remember what sort of operation it is. This one. Okay, this type of operation is, as we know, a binary operation, right? It's a binary. It implements a binary operation. Binary operator. This particular lambda expression implements a binary operator, and it implements this addition operator. Okay, so binary operator interface. Okay, so now we can go and specify our SAMs, our SAM implementations in terms of lambda expressions. Okay, in Java, and that's how we're going to do this. Okay, this is one thing, right? So it's a binary. We can go and replace this entire thing like this. So now look how simple it is. How simple we can go and specify a binary operation, and a particular one, which is the addition or something. Now, what is this guy? Okay, this is also a lambda expression, but it implements a consumer, right? It implements a consumer. It implements a consumer because it takes a value, right? But it doesn't produce anything. It produces void. This particular expression just prints out. It is doing something. Again, this is called, okay, it's changing the state of our program. Okay, it's doing something mutable. This guy is not doing a mutable. It's taking all of its input from the function, and it's doing something with the inputs and then returning the value. It is not dependent from the external world, and this is sometimes called a pure function. Pure function. It's a pure function. This is a pure function. It doesn't depend on anything from the external world. It takes everything from it as an input. It does something there and then spits it out to the outside world. This guy is not pure because it depends on this class, which in turn changes something externally. It's changing something on my program state, right? So, and consumers and suppliers are normally functions. The opposite of the pure function is a function with the side effects. It's function with side effects. Side effects. So this function is a function with a consumer, and this is a supplier. You guys understand this is a supplier. This is a consumer. This is a supplier. These functions, because they just take some value and they just go and make change in the state of the program, and particularly just print out something to the screen. And this guy, okay, is can be done as called a supplier, but basically it produces void. Okay, doesn't produce anything. It's both supplier and a consumer, I would rather say, because it doesn't take any value, right? And it still goes and makes change, okay, in the state of the program, right? And or I could have, if it was a supplier, I could have taken the values from, let's say, from some array variable, right? That would mean that this function is a supplier. Instead of going and printing it something out, I would have rather said, okay, let's say return and then the name of some variable that is not passed to the Lambda function, but is available, okay, in the scope of this variable, in the scope of that particular class. Okay, so now we specified the lambdas. Lambdas, they implement these functional interfaces that we specified. So what we're going to do with them? Why do we need these lambda expressions at all? So now we're going to use these lambda expressions to build our pipeline. Okay, so the pipeline is the task that we would like to execute in terms of a functional programming, okay, language. So we specify the task with this set of operations, with a sequence of operations that we'd like to, okay, run. So what sort of operations we have in a pipeline, right? So okay, first of all, the pipelines are represented in Java with the help with an object called stream. Okay, there's a stream object, stream interface, which represents a pipeline in Java. So pipeline is just some you can go and imagine some sort of a pipe, right? So it has both, okay, beginning and the end. So some data comes into this one. Let's say data 1 comes out into this pipe, and then some data comes out of it. And anything that happens here is just the transformation of the data. This pipe doesn't have access to a memory, doesn't have anything to this one. So the pipe simply goes and manipulates the data and spits out something else. So now, when someone says, okay, when I'm doing functional programming, they just build this pipe. The pipe will contain certain, okay, like operational units, right? And these operational units do some operations on the data that flows through this pipe. Okay, so normally the pipes begin with a data source. And the data source in Java is something like some mutable state, some array, right? So, and then it performs various intermediate operations on that data source, and then ends with some terminal operation, with single terminal operation. And this terminal operation can decide what to do with the data that is coming through this pipeline. So the stream pipeline is formed by chaining the method calls, right? So we have to chain the method calls in a certain way to indicate what we want to perform, what is our main final job. So the streams do not have their own storage, as I said. They don't go and do anything mutable. They cannot be reused. Okay, once you use the stream, once you pass the data through this stream, okay, you cannot repass again all the same data again. Okay, you have to give a different data source or maybe the same data source again, and then make the pass again. So the streams are also lazy, which means that once you go and specify the task for your program, it doesn't mean that the data will start flowing through this pipeline as soon as you go and create this pipeline. No, the data will be flowing through this pipeline only when the terminal operation is invoked, only when someone asks for the data. Okay, when someone says, okay, give me the data, and now the stream starts sucking the data from the data source, and as it sucks the data, it goes and transforms the data as you wish, and then gives you the data in a different shape. Okay, so the intermediate operation is, as I said, lazy. They are not executed until they are something that is in between, and the terminal operation is something that is at the end of your stream pipeline. Okay, so let's take a look into some intermediate operations here. So we got filter, we got distinct, limit, map, and sorted. So these are the most commonly used intermediate operations in the stream of data, right? So there are a bunch of intermediate operations in the pipeline, as we discussed. So they have certain, they take these intermediate operations, they take different type of functional interfaces, the SAMs, implementation of SAMs, and and they do their particular operation. For example, as the name suggests here, the filter one takes a predicate, okay, and then returns elements that satisfy the condition. Okay, so you can pass a particular value into the predicate and then get true or false, and then if it's true, then the value will be kind of passed through the pipeline to the next intermediate operation. The distinct intermediate operation is the one which basically lets the unique elements only, right? So there are one more thing that you would need to know about the intermediate operations here. So the intermediate operations, they can be classified into two types of intermediate operations. The ones with the stateless ones. So the filter one is called stateless intermediate operation, because in order to make the decision about whether to let this particular element flow through the pipeline or not, okay, it's not dependent on other externalities, on other elements, okay? So it's not dependent on a particular state, okay? So you can go and look into the particular element, and if it satisfies your condition, it basically flows through the pipeline, right? The distinct intermediate operation, on the other hand, is called stateful, okay? Because in order to make decision whether you would like to let this particular element to go through the pipeline or not, you should look into the entire data set and then make the decision, right? So if this element is unique or not, so it can keep some state, right? So once it lets the element through the pipeline, it kind of keeps the record of such element somewhere, right? And if another element with the same kind of value comes to the pipeline, okay, it will not let this element flow through this pipeline. So it goes and maintains some sort of a state in order to make sure, okay, to make a decision whether to let this particular element or not, right? So the limit, okay, is an intermediate operation, and it is also a stateful one, right? Because it has to keep track of, okay, how many elements it has let go through the flow. So it basically decides how many elements should flow through the pipeline, and anything that exceeds this limit will be blocked, okay? So you can decide, okay, like I want only 5 elements from this data set, right? So you can use limit, and then you can pass here some integer, okay, some number, and then decide whether you want this one to take this element or not. The map intermediate operation is, on the other hand, is stateless, because what it does is it converts one element into a completely new element, okay, into a completely new type. So it just maps one element to a different set of elements, and you decide the logic. So the distinct doesn't take any argument, right? Doesn't take any SAM. Filter takes a predicate. So filter takes a predicate as an input. Distinct doesn't take anything. Limit takes just a number as an argument. And map takes a function, right? It's a function SAM. So the function SAM is, it's T and R. So it takes something as a value of T and then returns something as a value of R. And it is stateless because in order to convert one element to a new element, it's not dependent on the rest of the values, okay, in the set. Sorted, okay, again, there are two versions of sorted. You can call sorted, and it will use its natural comparison algorithm to make sure how to compare elements. But in general, the sorted can take an argument, a binary operator, some binary operator, okay, which takes some values, two arguments, and then gives you some integer. Okay, so this is called a comparator, and the comparator is okay, something that tells you whether a two numbers is greater or equal or less than or so forth. Okay, so comparator is a comparator interface comparator has a method called compare, right? So it has a method called compare, sorry. Yeah, so it's integer compare, and it takes, let's say the comparator is t, of a type t, takes two arguments of a type t, right? arg1 and arg2, and as you can see, it returns some integer, right? So this integer, if integer is equal to 0, so let me go and say if result is equal to 0, then these two arguments are equal to each other. Okay, this means arguments are equal to each other. Okay, if it's a positive number, if it's greater than 0, okay, so it is it's a positive number, so it's a positive, any positive number, then it means argument 1 is greater than argument 2, and the negative, as you know, okay, it is the opposite, right? So by just sending like any positive integer or any negative integer, you can tell the comparator, okay, whether these two arguments are greater than each other or less than each other, or they're equal to each other, right? So this comparator is just again another functional interface which can be implemented as a Lambda function, right? Because it just has a single method called compare, and it can be implemented. This SAM can be implemented as I wouldn't say it's a binary operator, because it takes something as t. Yeah, it's not a binary operator, so sorry for this mistake. It is just a comparator. It looks like a binary operator, but it's not, because it takes two arguments, but it returns an integer. Okay, the value is always integer. It's not t. In a binary operator, the outcome is also t, right? So it's not a binary operator, sorry. But it takes two arguments, and it compares these two arguments and returns some integer value. So it takes something like that as an input, and again, this can be again implemented as a Lambda method, and the Lambda method, okay, you can go and implement something like this as a Lambda method, and then this one. And as you may know, okay, the sorted is also stateful intermediate operation. Why? Because like you just need to look into the entire data set to identify the position of a given element, okay, in this particular data collection, okay, and that's the reason. So you need the sorted intermediate operation needs to maintain some sort of a state within itself to make sure which element is bigger, which element is not bigger, and so forth. So the implementations of this sorted operation, they have certain state involved in this particular method. Okay, so there are oops. So these are the intermediate operations, common intermediate operations. There could be another one called take, and then skip. Sorry, the skip take for doing some pagination operations. So you can go and check the documentation, the official documentation for Java, to get the complete list of intermediate operations you can use while building the stream pipelines. But these are the ones that are commonly used in Java. Okay, and along with the intermediate operations, we have terminal operations, and the terminal operations are usually placed at the end of the pipeline, right? So end of the pipeline, and they may yield a value or may not yield any value. Okay, so for example, the for each doesn't yield any value, no, returns void, no value. Okay, but it does certain operation. Okay, it can be described as, again, lambda function or anything. It does certain operation on each element of the pipeline. Okay, so it could be like a printout, some printout statement, or maybe some some lambda method with a side effect. So it goes and mutates, modifies something, okay, outside the method itself, like something inside the class or something like that. Again, something with a side effect, some method with a side effect can be placed into the for each method. So again, it takes some consumer predicate, sorry, not a predicate, consumer SAM, okay, of a type T. Okay, so it takes some value of a type T, but it doesn't return anything. Okay, so that's a terminal operation, and it takes consumer as an argument. Okay, so the average, count, max, mean, they just return a number, right? So it could be double, and it's double. So they return double, right? So what they do is they basically aggregate the values. This one returns an integer, but max, mean, again, can depend on the data type. Average is double, so it is some numeric value, right? So depending on which method you're calling, okay? So these are the ones, and they normally don't take any input, okay? They just simply take the, find out the maximum or minimum values. Okay, the reduce is also a terminal operation, but the reduce has following signature. So it has two arguments. Okay, it's not just a single argument. The first argument is called identity, and the second argument is called, its second argument is some binary operation. Now it's definitely binary operator. Okay, of type T. Okay, so how does reduce work? So using reduce, you can go and create any customizable aggregating function. For example, you would like to find the product of a given set, right? So what you can do is you can use reduce, and then you can say reduce, for example. So identity is some value that will not change if it's applied. Let's say, the implementation of the binary operator. So the binary operator can be implemented as x and y in Lambda, right? And something you do with the x and y. So let's say it's a multiplication. So if you say x and y, so this is your binary operator, right? It's a multiplication. So the identity for this binary operator will be 1. Because if you go and apply the first element to the identity, right, then the value won't change. And the identity for the summation, it will be 0, right? So it won't change if you apply the identity for this particular, with the first element in the list. If you apply this identity and the first element in the list, okay, in this particular data set, if you apply the binary operator to the identity and the first element in the list, right, then the first element should not change. It should be the same value, right? So you need to just go and define your identity value, right? Whichever value it is. It could be number, it could be something else, depending on which binary operator you're using. Okay, and then decide the identity operator. So then if you go and say, so let me go. So if you go and say x, y, x multiplied by y, then what it will do, okay, it will apply this method, this binary operator, to each element in your list. The first element is x represents the element in your list, right? This is the element in your list. Y represents the current result, the cumulative result that you have right now. So this will give you product of all elements in your data set, right? So okay, so you have to apply the identity and the method, the binary operator, something that does it. So x represents the first element, y represents the cumulative result, right? And then you're simply just doing the operation for each element of it. Y gets passed to the next element and next element, and then as a result you got to have the entire product of all the elements in your list, right? So in your data set. Okay, so that is how you can go and create any customizable, okay, aggregation functions you want, okay, using this reduce method. And also now we have other terminal operations which generate collections. So they go and create immutable states. Okay, so some data set that can be modified and accessed like randomly, right? So it is any instance of a collection, right? So the collect keyword gives you a list, a set, or any collection, anything that we discussed in the collection set. So it basically gives you any instance of a collection, collect method, and it requires as an argument something called a collector, some instance of a collector. Okay, so collector is a class which implements different ways of accumulating the elements coming from the pipeline. You can create your own collectors by overriding the collector, okay, collector class. But there are some ones like collector to list, for example, has the implementation. So collector to list, the static method, will return you a collector which will accumulate all the values into a list, into some array list, and then returns the array list as a value to you. Okay, so and then you can work with this array list. You can iterate through this array list, or you can do anything you want with this array list. Again, there is another one called toArray. This gives you, as the name suggests, just an array of elements. Okay. Good. So, and obviously this toArray is something that you need to be using for primitive data types like strings. I mean not the strings, sorry, the integers, the double or anything, right? Okay, cool. So yeah, and so let's go and talk about other things as well. Yeah, there are also other terminal operations which return you a Boolean value or a concrete element. So this gives you the element, not a collection. So the first element, which satisfies the predicate, that whichever predicate you pass into it, it gives you the first element, and this one gives you any element based on the predicate that you gave, right? So it's not necessarily the first element. Okay. So and any match and all match, this basically represents gives you as an output, and this one also gives you an element as an output. This one gives you, and this one gives you Boolean as an output. And what they do is they also take predicates as an input, and they apply. This one applies OR to all the elements in the list in the data set, That's why it's called any. And this one applies AND. Okay, this is OR, and this is AND. So it applies. This makes the disjunction by like combining all the predicates together, and this makes a conjunction by applying all the predicates to each element. Okay, so it makes a one big, like a Boolean statement for each element plugged into the predicate that you passed. Okay, so these are the important terminal operations you might need to, let's say, get certain important things in your code. So let's go and look into one concrete example. So we're going to go and create a particular instance of a stream. It's called an integer stream. You can also have long streams or double streams. Then we're going to look into the IntStream example. So in the IntStream example, we got a bunch of integers, integer arrays. And these integer arrays, as you can see, okay, can be converted into a stream. So using this off method. So once you pass this particular array of integers into this off method, this becomes a stream. Okay, it's a pipeline, the beginning of the pipeline. Okay, so in this pipeline we don't have an intermediate operation. Right after that we have a terminal operation called for each, and as you can see, the for each takes a consumer. It takes a value and it doesn't produce anything. Okay, so it basically prints out the values in the given list. So it's a pretty simple and straightforward example of building a pipeline. Okay, so some other examples, right? So you can go and use another terminal operation count, which gives you the number, or you can go and get a min or max. They return you, right, double. You can go and get them as so the min and max returns you optional integer, something called an optional integer. So optional integer means so you might get a result or you might not get a result. So if you don't have any values, then min doesn't know what to return to you, right? So it returns you not integer but optional integer. So this optional integer basically combines within itself, okay, two values, null and integer, right? So if you want to get the integer part of it, you have to call the getAsInt method. But okay, if the value is not, if there is no integer, but if you calling getAsInt, then it's going to cause an exception. It's going to give you okay, the unsupported value exception. Okay, so this one is also the max. It returns you an optional integer in a different type of object. And then we got average. Average returns the optional double. And then you can go and get the double part of it, not the null part of it. Double. If there is a double part of it, you'll get the double part. If there is no double part of it, then you're going to get an exception. Okay. And the reduce, as we talked about, that reduce just does the summation. Okay. This does the squaring. Okay. Seems like I made a mistake here. X is the Y is the one which represents the element. Yeah, I made a mistake here. Sorry. So this is the opposite. Okay. So this is not the cumulative element. Y is not the cumulative element. Okay. This is the cumulative element, and this is the element itself. Right. So. So in this case, yeah. So the cumulative element is equal to the identity for the first element, and it is equal to whichever value that it generates at the end. So I just messed up a little bit in the way how I designated the attributes. So in this case, the cumulative element is just the first element. Element itself is the second element, and now I can see. Okay, here you can find the sum of squares for each element. Okay, so by just creating this particular reduce method. Okay, so just beware that okay, X is the cumulative element, I is the element itself. Okay, good. So yeah, this is just a product. That's what we saw. Again, we are not implying any particular intermediate operation here. We're simply using the reduced method, the terminal operation, to get some value, and this value is getting yielded into some integer in this case. Okay, we can go and also use some intermediate operations here. So the intermediate operations like filter and sorted. Okay, so the filter, as you can see, it takes a predicate. It checks if the value is even number. Okay, if it's an even number, then it lets all the value. It takes all the values here, and then it from the filter it just filters out only the even numbers. And then this one sorts all the even numbers that coming out of this filter, right? And then you're simply printing them out to your screen, right? So that's something that basically you can go and write down in one simple statement, okay? The other one is, okay, here what you're doing is you're checking if the number is odd, and you're filtering all the odd numbers. The odd numbers are passing, even numbers are staying here. So then you're getting the odd numbers and multiplying them by 10, right? So you're applying some function. In this case, just multiplying by 10. So then you're sorting them by, again, and then you're printing them out as usual. Okay? You can go and generate streams, not just from an array using of, but you can go and use the IntStream's range method to generate a stream of like sequential values, right? So from 1 to 10, where 10 is not included, if you say range closed, then 10 is included as well. So, and then you can say sum, it basically sums up all the values. So range function generates you a stream of numbers, doesn't generate you an array of numbers, okay? Don't get confused when you don't get an array. If you want an array of numbers from 1 to 9, okay, instead of using sum here, you have to say to array, and it gives you, okay, an array of numbers from 1 to 9, okay? Range generates you a stream, and then you can apply either any particular intermediate operation or a terminal operation to this stream to get the result that you would like to have, or you want, okay? Good, so we talked about all these things, okay? And then you can go and read out it from the slides. Everything is explained here. So you can also create the streams for any data types, let's say for integer, by using the arrays stream method. And in this case, you just go and create an array of streams. You can go; it can be an array of customers or whatever, and then you can go and pass this data source to the arrays stream method. If you go and pass this data source to the arrays stream method, it goes and creates a stream of, let's say, these values, right? And then, again, you're not specifying how these values should be accessed, like in this sequential order, in a reverse order. The point is, okay, it's irrelevant to the operations that you're doing. All you need to do is you should be able to specify the task, okay? So what you're doing is you're sorting them, applying the intermediate operation sorted, and then getting the collected array, okay? So another one is called greater than 4. Again, I think it's self-explanatory. The only here I'm using the collectors. Okay, the collectors is the helper class for getting collectors. The concrete implementations of the collectors, collector classes. So toList returns me a collector class, which again aggregates all the accumulates all the values into that particular data set, right? Into that particular collection, and then returns that as a mutable state, as something that I can go and access and read and then and modify. Okay, so so everything is clear here. Again, you're getting values getting higher than 4, and then sorting them, and then getting them into a different array, a different list. Okay, cool. So I hope this one is kind of concept is using arrays stream method is also clear to you. You can go and use the same thing for strings. Okay, but there's one more thing that I'd like to point out. Like you can go and define your own Lambda operations, or you can go and refer to the concrete implemented methods using this double semicolon notation. Okay, so there are two cases you can go and do this. Three cases you can do this. Okay, this two uppercase method is an instance method, right? So we know that we can apply this method. This is the method of any string object, right? Two uppercase. I can go and say, for example, Sarvar is just an instance of a string object, and I can go and say two uppercase, right? So if I do so, right, what I'm doing is I'm calling the instance method of this object, right? So if I go and if I want to refer to the instance method of the object, so how this particular method will be executed, if it's an instance method. So let me go and write instance method. If I'm referring to an instance method of a string class, then this is in fact is equal to, this method is equal to x to uppercase, right? To uppercase. So this particular notation that I'm writing here is equivalent to this notation, right? It's equivalent to this notation. Okay? If I'm calling the instance method, okay, what if I call instead of here I call something like not the instance method, but the class method. Okay, so let's say I got a class method called format. String has a class method called format. I can say string format. Right? This is the class method. So instead of doing this, if I go and say string format, here if I go and write string format, then this will be equivalent to, this is the class method, right? This is the class method. It will be equivalent to, so I got an element as x, right? So it will be equivalent to string format and then x. So it passes the value like this, right? It won't call the instance method like this, but instead it'll pass the actual value to the static method of the class that you're calling. Again, you can reference both instance methods and class methods in the same way using double semicolon. You're basically referencing these methods, but they are just the shorthand notation for this particular Lambda expression or this particular Lambda expression. Okay? So, and there's also one more thing that you would like to do is called string new, and this is basically, or it could be customer new or something. So this basically refers to, okay, basically creating a new customer. So it can go and, okay, be equal to something like new string. And let's say the string gets some argument or not. Okay? If x is not equal to anything, then it doesn't get any argument. It basically calls the no argument exception. No argument constructor. Okay? So you can go and create new elements, new objects by just referring to the new, okay, the constructor like this. Constructor like this. So this is basically equivalent. In this case, it is a constructor. So you're referencing the constructor. So there are three things you can reference like this: the instance methods, the class methods, or the constructor. Okay? And again, because you're using it as a map, it basically generates, it takes a value and it generates another value for you, right? Also, sorted, as I said, sometimes it takes a value. I mean, it doesn't take any value, but sometimes, as I said, it takes an instance of a comparator class. Comparator. Not comparable. Okay. Not comparable. Like if I want to make sure that my elements are comparable, I have to implement a comparable interface, and it has compare to methods, right? It's different from comparable interface. It's not comparable interface. So you can go and check the comparable interface as well. It's a different interface. Comparable interface makes your elements, your custom classes comparable. Like you can go and use logical operators, okay, to compare these elements, okay. So if your element implements a comparable element, if your class implements a comparable interface, then you can use this this logical operators, relational operators, to compare the elements, right? So these are relational operators, not logical operators. So these relational operators, you can go and use them to compare and to get this one. But comparator is just a class which takes two elements and then returns an integer, right? And we discussed about the way how this comparator class is defined. Okay, so we can go and define, you can go and kind of implement your own comparator instance, or you can use the ready-made enumerator. So the string contains a constant, enumerator constant called case-insensitive order, and it is basically a comparator. Okay, it's an object of a comparator, which implements this comparator class. Okay, and then you can simply go and use this particular method to get its comparative method. So case insensitive means it doesn't take into account the case when comparing the strings. Okay, or you can go and define your own comparator using the lambda expression, as we saw there, using x, y, right, which returns some integer. Okay, so something you go and write. Sometimes it is x minus 1, y. So if it's just two numbers or whatever, so it basically generates some integer. Okay, so you decide which integer to generate. You can go and write some if statements, perhaps, to decide if it's a 0 or a positive number or a negative number, and so forth, depending on what you're comparing and how you're comparing. Okay, and the collectors list is again just an implementation of a collector class. Okay, so the same goes here. You can go and call the reversed method to get the opposite comparator, which basically changes the order of your sorting. Okay, so hopefully that is clear too as well. And then here I explained the different ways you kind of call instance methods, object instance methods, right? So, oh, by the way, there's a fourth method as well. If you go and reference, you indicate a concrete object and reference its instance method, then it passes that x value that you're getting from as an input into the object method of this one. So let me go and write that one here. So there's fourth one as well. I forgot to include this. So there's fourth one as well. In the fourth one, you're indicating the concrete instance. Let's say, I don't know, string has, what string has, let's say Sarvar, and so let's assume for example's sake that it has an append method. I don't know, I mean, I don't think it has an append method, but let's just, for the sake of an argument, let's assume that this is an instance, right? Sarvar is just an instance of a string, and I'm referring to append method using, again, double semicolon notation that this is equivalent to. Now, these were classes, string, string, and this string were classes, class names. But I can go and reference the the instance method of an object, not of a class, right? So how this will look like, so obviously, as you might guess, this will be translated into something like Sarvar append x, right? So it basically, whatever it takes the value, and then if it yields any value, it passes it on to the next intermediate operation or a terminal operation. If it doesn't yield any value, let's say append doesn't return any value, it returns void, and obviously this collector is not going to collect anything. Okay, so but let's assume that append appends the value and then returns the new string, okay, as an output. Then in this case, okay, so we are getting all the new values from here, and then we are appending all these values to server, something like that. Something like that can be happening if I write down, instead of this, I write down something like that. Okay, so this is just the fourth way of using the double colon notation, okay, to reference the methods, okay, that are implemented. Okay, good. So we discussed about that. These are some examples. Okay, as you can see, we are referencing the instance method. This is the instance method. Okay, this is the instance method. This is also an instance method, right? So we got an instance of out, and we are simply using this out is our standard out, right? This is just some instance, some object which represents our standard out, and we're calling its println method. So it's an instance method. Okay, this one is a static method, okay, or class method. Okay, and this is a constructor. So we can go and do refer to the constructors and everything like this. Okay, cool. So yeah, we talked about this different ways of sorting. Okay, there's another example here for working with the employees. It's a custom class. Okay, it has its properties like this. And how can we go and create a stream out of this custom class? Let's say we'd like to print out our employee. But if you want to print out your employee, first of all, you need to overwrite the toString method of your object, which prints out all the properties of your object. Okay, and then you can pass that object to println method, and simply goes and prints out all the elements there. So in here, what we're doing is we're basically creating an array of employees, right? And then we're getting these employees as a list, or we could go and pass this employees, okay, without basically creating this. We could pass this array of employees into the stream method as well, but we basically decided to go and create a list here, okay, and then call the lists stream method to get a particular stream. Yeah, so this could be replaced with something like that, right? So you know, arrays stream. This could be also replaced like this, but you can also go and call the stream method, instance method of the list itself, which creates a stream and connects this data source to the beginning of the stream, and then you can go and define your stream, the pipeline, the way you want. So here we don't have intermediate operation, we have terminal operation, basically prints out all the elements in this one. And we can go and do something else. Okay, we can go and define our predicates as variables, right? A predicate or any SAM implementations, okay, any SAM instances, okay, those functional interfaces, those instances, we can go and define them as variables, and then we can assign the variable to a Lambda function, right? This is just a Lambda expression. So you can understand what sort of Lambda expression it is. Okay, so again, it's a predicate which takes an employee and returns a Boolean value. So E is an employee. You can go and call the getSalary method and get this one. So basically, it returns true if the salary of the employee is within this range. Okay, and then you can use this particular predicate anywhere you want. This particular variable, which represents a predicate instance, wherever you want. Okay, so you pass it to the filter because filters take predicates, and then you can go and create a comparator object. Okay, by calling the static method of comparing, and then pass the field. Okay, so this getSalary here is just represented as some Lambda expression, as you know what sort of Lambda expression it is. It is x. Okay, this is equal to x get salary, right? So it gets the salary. So the comparing returns us a new instance of a comparator object, right? And the comparator object that will tell how to compare the values. So it basically does the subtraction. Okay, so it basically does it implements it in a default way. So it gets the value here, and it does the simple implementation, as I said, x minus 1 implementation of the comparison. So and then you have the comparator class. If you have some more customized comparator, then you can go and implement your own comparator for the employee class, okay, and then decide how you're going to compare employees at all. Okay, so you basically need to pass some comparator to understand which employee comes first and which employee comes next, and simply print out all you want. Okay, you can go and get the first element like this. Get, by the way, is another terminal operation. I forgot to mention the get is sorry. Get is not a terminal operation. It's a method of the optional class. So optional. So this returns an optional class. So sometimes basically optional is something that combines the value and the null, right? So get goes and gets the value for this optional. If there is no value, then it's going to cause an exception. Okay, so you can get the particular, let's say, employee that is satisfy your particular condition like this. Okay. Yeah. Some other examples for selecting, let's say, for ordering employees by, by their, for example, first name and last name. Okay, so you can go and create a combined comparator, right? So by just let's say passing the get first name and last name using the comparing method, and then comparing is the second. It goes and checks the last names first, and then so it basically does the lexicographical comparison here for the string, right? And then if this ties, it goes and compares the second function. Okay, so this is kind of, there is a tie between these two elements. It goes and uses second field for finding out the position of the employee, right? So in this way, you can go and create a generalized comparator, okay, which combines these two fields, okay, and then use it to sort your elements. Okay, if you want things to be in the reverse order, then you can simply call the method which will reverse your comparator in this direction. So you can see that it works as follows. Yeah, you can go and call the distinct method to get the distinct elements based on the last name. Okay, so note that, okay, if you go and call distinct method on the employee distinct method doesn't know how to compare your employees. It basically goes and compares them by their reference. So even if their names are the same, they could be the same, different objects, right? So distinct will not tell that these employees are distinct. It will think that it is the same. So you have to tell which parameter, okay, you're going to use. So in this case, what you're doing is you're extracting the last name of the employee, and then because it's a string and Java knows how to compare the string and detect if these things are equal or not, okay, it goes and uses the distinct method to figure out if these two strings are equal. If they're not equal, then it's going to pass. If it's equal, then it's going to not let the duplicate ones. Okay, so and then sorted and then print out. So you're going to get a distinct list of last names in your employees list. Okay, so here you just get the name of the employee, but first you're going to sort them, right? So you can go and do this. You can use map to get concrete values here. Okay, so yeah, so you can have like multi-dimensional arrays as a result, where you can group by things. Let's say, so every group will be determined as a one list. Okay, so you can have list of lists, and for each list you're going to have a particular like each list within a given list. They will be split by their particular department number. Okay, so you can go and use this grouping by implementation of the collectors. So it basically collects your data in this particular way. So you can go and look into this, okay, example as well. So basically, you're getting the elements and then you're printing out, okay, for each department in the department list. You're printing them out like this, right? So yeah, so it's basically a tuple in this case, right? So it's a tuple for department and the employees in the department. So, and for each you're getting this not one single element, but you get two elements, the grouping element and the actual like a array which contains the values, right? So you're printing out the department and you're iterating through the elements inside this department using this printf again. And it's going to print out something like that. Okay, yeah. You can count the number of departments. Okay, a number of employees in the department using this again grouping by here, and then here you're basically saying which fields you would like to have, which kind of aggregating functions you would like to use. So you can go and use the counting method. So it basically groups the employees by their department name, but and then counts like how many let's say employees in the department, and as a result you're going to get something like that. Yeah. Okay, so they got some intermediate operations like map to double. So it basically both gets the value and then tries to parse it as a double. Okay, so if it's some integer or something else, it goes and parses it into double, and then you can sum it up like this. Yeah, and the reduce, we talked about that. So basically map to double, you get a double out of it, and then you can simply sum up all the salaries for the employees in your set. You can get the average employees as well. Okay. So this example shows you how to parse the line of a text from a file. So you can go and get the current path to a particular file here, and then you can use this files namespace to read the lines of the file. So that it is going to return you a string array. So this string array, the string array is going to, you can go and iterate through each line of text by calling map. So you get a line, and then you can do some manipulations with the line. So it gives you like basically removing all these elements from the list, right? And then the flat map is basically going to join all the lines coming into it. So how are you going to join all the elements? So you can see that like in this year this map file takes a function, right, with input type t, and then it returns something with an output type R, but in this case both of them are the strings, right? So it's t and t, doesn't matter, right? It's just a specific case. In a flat map we have a function which returns something with the type t, but takes something with the type t but returns a stream. Okay, so let's replace this word stream with some sort of an array, let's say. So we know that this parent split, it gives you an array instead of a single line, right? So and the result will be, if you go and use the collectors, it will be just for every line you have, let's say, words, like bunch of words, right? So you're gonna have like array of arrays here as a result, right? So obviously you don't want like this kind of like two-dimensional array to be in your as a result. So instead of going and creating a two-dimensional array, but and just having a single-dimensional array where you just want to have all the words, you don't want to have words grouped by their lines. Okay, so then you can go and use the flat map. So what flat map will do is, like, your function generates an array, but instead of passing the entire array to the next intermediate operation, it just passes the elements of that array one by one. Okay, so like flat map is different from map because map simply gets the output and passes it to the next intermediate operation. Flat map gets one single element, generates an array, but it doesn't pass the array to the next intermediate operation. It simply pulls every element of that particular array, resulting array, and passes it like one by one to the next element. So in this way, when you're doing the collect, you're getting something like a one single dimensional element. Okay, so that's the place when you have to use this flat map intermediate operation. And and you don't have to return arrays here. You have to return something like a string. So if you have an array as an output, convert it into a stream and return it as a stream. So because like you connect one stream to another stream in this case, right? So this array, if your Lambda expression returns an array, convert this particular array into a stream. So in this case, we can conveniently use this split as stream method, which kind of converts the resulting array into a stream, okay, and then returns it to the next intermediate operation. And the next intermediate, we don't have an intermediate operation; we have a final operation, which basically collects all the input into the tree map, into a hash map, right? So into a tree map where we can let's see how many kind of occurrences of a given word we have in this text, like how many dogs, how many if we got a word dog, okay, how many dogs we have, how many cats we have, and so forth. So like the frequency for each word, we can go and calculate it using this simple particular stream. Yeah. Good. So hopefully, as you can see, the result is the word and the number of occurrences for a given word. Okay. So so we can go and list through every word count as an entry set. Entry is just a key value pair, right? So it's a string and an integer, and we can iterate through the entry sets as well. Right, so with the stream that we have, so we can go and run these collectors and grouping bys to do certain operations with them. Okay, so as a result, you might go and get something like that. So basically, it gets the first character out of it, and then organizes the entries like this in this form. Okay, so I'll upload these examples, okay, for this lecture, and then you can also view the code and then play with it in free time. Okay, so we discussed about that. We discussed about this random input stream. Okay, it's basically so this secure random generator generates 6 million numbers between 1 and 6, right? And then we're calling the box method to convert these primitive integers into object representation of the integers. And then we can go and use the identity method. Identity means like it basically gets the value and returns the same value. So if it's 1, it's just 1. It's 2, it's just 2, and so forth. So and basically counts. Okay, if it's counting 1, then it will be 1, and it counts how many ones we have, and then so forth. So as a result, we can go and print out the tuple with the phase and the frequency, and then see like how many ones we have, how many 2s we have in this particular dice throw, let's say, right? Okay, this is just one example. You can go and look into this one. Yeah, one more thing that you can do with the lambdas is you can go and write event handlers using lambda expressions. Let's say this action listener in Swing. It's just a functional interface, right? It just has a single method called action performed. And you can go and, instead of going and implementing this entire interface with an anonymous class or something, you can simply go and write some lambda expression which implements that single method, okay? And it is kind of easier than going and writing down a lot of code. By just going and writing down a lambda expression would be, let's say, shorthand notation, and reduces kind of readability, makes your code readable and reduces the amount of code you write. Okay, so these are just some syntax sugars to take into account. So thank you for the attention. Sorry for this long lecture, but I hope it was informative. See you next time.